Hello, Matt here from chemistrystudent.com. In this video, we're going to look at total entropy. We're going to talk about what total entropy actually is, how the entropy change of a reactant system and its surroundings are linked, and look at how we can use total entropy to predict whether a possible reaction is feasible. Enthalpy, entropy, and entropy changes have been covered in separate videos. Check the links in the description below. Before we talk in detail about total entropy, it is essential you are comfortable with enthalpy and entropy and how they can change in a reaction. As a quick recap for this video though, enthalpy is the energy content of a substance or system. Some of this stored energy can be released and flow out of the system in the form of heat and is considered useful. The rest of the energy is arranged amongst the particles in such a way that it is unavailable to flow out as heat. It is essentially unavailable energy that can't be used for anything useful, and is called entropy. The entropy of a system is based on the possible arrangements of particles or disorder within the system. Every substance has its own value of entropy as particles in different substances are ordered in slightly different ways. And this means energy is distributed in the substance differently. Entropy increases with the level of disorder and possible arrangements of particles in a system. Units for entropy are joules per Kelvin, as temperature changes the possible arrangements of particles within a system, meaning it changes the distribution of energy. Increased temperature means increased entropy. When a reaction happens, the combined entropy of the reactants will be different to the combined entropy of the products, as each substance will have its own standard entropy. This means the entropy of the reactant system will change. This entropy change can be calculated by taking the sum of standard entropies of products and subtracting the sum of standard entropies of reactants. Standard entropies refer to the entropy of 1 mole's worth of a substance under standard conditions, 298 Kelvin and 100 kilopascals. The units for standard entropy are joules per Kelvin per mole and are shown with a capital S for entropy and the little round circle showing standard conditions. All standard molar entropies are positive values. In chemistry, if a reaction is feasible, it means it can theoretically happen, based on energy changes. In other words, it's allowed to happen. At this level, the word spontaneous is also sometimes used instead of feasible. Be careful, however, just because a reaction can theoretically happen doesn't mean it necessarily will. There are other factors such as activation energy and rates of reaction that may mean a theoretically possible reaction may never actually occur. Recap done? Let's go. When particles react in a chemical reaction, they are usually surrounded by other particles that aren't reacting. For example, if you burn a candle in air, the combustion reaction occurring between the fuel in the candle and oxygen is taking place surrounded by lots of other particles in the air. Molecules of gases that have no part to play in the reaction but are simply there. It's the same for a reaction in solution. When a reaction occurs between aqueous particles, they are surrounded by water molecules that don't actually react, but are constantly around the reacting particles. When studying energy changes for a reaction, we describe the reacting particles and products formed as a reaction system, often just referred to as a system, and the particles around the reaction system as the reaction surroundings, often referred to as surroundings. As heat energy flows out of a reacting system in an exothermic reaction, it flows straight into the surroundings, increasing the temperature of the surroundings. Equally, if heat energy flows from the surroundings into the reacting system in an endothermic reaction, the temperature of the surroundings decreases. These heat energy changes are straightforward to measure. When predicting the feasibility of a reaction, however, it isn't just the overall enthalpy change of the reaction system and surroundings that we need to consider. It is also the entropy changes of both. For any reaction or process to be feasible, the entropy of the entire universe must increase. It can never decrease. Now, the universe is a pretty big place, and taking the whole universe into account when thinking about a small reaction in a beaker of water isn't really very practical. Instead, we have to treat the reaction system and its surroundings as a mini-universe where nothing can get in or out. We know this isn't quite true, as a beaker of water, for example, will still exchange energy with its own surroundings, but we have to draw the line somewhere. In thinking of our reaction system and its surroundings in this way, almost like a perfectly sealed box, we know that in order for the reaction to occur, the overall entropy of everything inside the box has to increase and have a positive entropy change. This total entropy is made up of the entropy of the reacting particles, the reaction system, and the particles in the box that aren't involved in the reaction, the surroundings. The total entropy change that occurs is going to be based on the entropy change of the reaction system and the entropy change of its surroundings, giving us an equation. Change in total entropy equals change in entropy of system plus change in entropy of surroundings. More conveniently shown as delta S total equals delta S system plus delta S surroundings. Remember, for a reaction to be feasible, the change in total energy, delta S total, must be a positive value, meaning when delta S system plus delta S surroundings are added together, the value must be positive in order for a reaction to be feasible. The change in entropy of the system can be determined by using the standard molar entropies of reactants and products. Entropy change equals sum of entropies of products minus sum of entropies of reactants. The change in entropy of surroundings is based on the enthalpy change of the reaction and the temperature at which the reaction occurs. This is because as heat energy flows in or out of the surroundings, the distribution of energy as entropy will change, and we know that entropy is based on temperature, joules per Kelvin per mole. This can be shown mathematically as delta S surroundings equals minus delta H, enthalpy change, divided by temperature. By substituting in this solution for change in entropy of the surroundings into the total entropy change equation previously shown, we can see that the change in total entropy, delta S total, equals delta S system plus or minus change in enthalpy, delta H, divided by temperature. It's now easy to check if a reaction is going to be feasible by making sure that when we use actual values in this equation, the answer for change in total entropy is a positive value. If the value calculated is negative, the reaction isn't feasible and can't occur, as this would mean a decrease in total entropy. You need to be careful here of units. Entropy is given in joules, and enthalpy is given in kilojoules. Enthalpy must be changed from kilojoules to joules to find total entropy change. This idea of total entropy and total entropy change explains why reactions that have a negative entropy change of system can still occur, because the reaction process overall can cause an increase in the entropy of surroundings. As long as the increase in entropy change of the surroundings is bigger than the decrease in enthalpy change of the system, the reaction is feasible. Be careful, mind. The fact that a reaction may be feasible at a particular temperature doesn't mean that it will definitely happen. A high activation energy barrier, for example, may mean the reaction, although feasible and allowed, isn't actually going to happen. So, to summarize, both the entropies of reacting particles and their surroundings change during a chemical reaction. Total entropy change refers to the combined entropy change of both entropy of the reacting particles, delta S system, and the entropy change of surroundings, delta S surroundings. The change in entropy of the system can be determined by using the standard molar entropies of reactants and products. Entropy change of system equals sum of entropies of products minus sum of entropies of reactants. The entropy change of the surroundings is based on the enthalpy change of the reaction and temperature. It can be represented as minus enthalpy change, delta H, divided by temperature, T. Using this and the total entropy change equation, total entropy change equals entropy change of system minus delta H divided by temperature. For a reaction to be feasible, the total entropy change must be a positive value. Remember to be careful when using this equation. Units for enthalpy change are in kilojoules and must be converted to joules by multiplying by 1000. Just because a reaction is feasible doesn't mean the reaction will definitely happen. Slow rates of reaction and high activation energy barriers may mean the reaction doesn't actually occur. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.